Now we are.
All right, I'm pleased to hear it. Thank you for joining us. We'll be blathering at you in a few minutes.
Wait. Never mind. Oh, okay.
So when I go to Fry's and try to get a display adapter large connector, is that just what I need to know, or do I need to know version 2.2 or display port on my Lenovo ThinkPad large?
Full-size display port connector. You won't find many of them.
I just need one.
I know.
And it's just a little short stubby adapter with the HDMI on one side and the...
Well, you might be able to find the adapter.
Is it a cable?
Also, Fry's superior. Typically, you'll have a cable with two DisplayPort connectors on either side.
Okay. So all of the DisplayPort connectors on either side, what will that do for me? Nothing at all.
Allow you to hook up to a DisplayPort monitor.
I don't have a DisplayPort monitor. I have an HDMI TV at home.
You want
an
adapter.
There you go. All right. So emails have been sent. Notices have been posted. Stream is live. Welcome to the afternoon half of the September SVFIG meeting. I'm Kevin Appert. I'm the program chair, and other pieces of furniture as required. I guess we'll have a couple of minutes of new things, rumors, announcements, gossips. Anybody got anything besides? Oh, well, there's Dennis. Hey, Dennis.
IoT, Windows 10 IoT on Raspberry Pi 2.
Okay. Is there a link that I could go to easily?
ms-iot.github.io. ms-iot.
Hang on a second.
This just came out, so it's all over with.
Yeah, the Internet of Your Things.
Yeah, UCASA as WeCASA.
Yes. There you go. It's just a Raspberry
Weather
Pi.
station using Windows 10. I remember in my youth working on things that were going to go to the South Pole, and it was like a 1802 with a battery. Yeah. It had to run off of this fuel cell converter.
It had more longevity than this.
Yeah. So this morning we were talking to things with Telnet, and it came up in this morning session, and I thought to myself, is there a Telnet client for my Android device? And there it is. There's an existence proof. There's at least one.
And I actually found a Microsoft Store app for Telnet.
Uh-huh. Actually, I went to Windows 7 help, and it's something you can go into your settings and turn it on. It's already in Windows 7.
It's been in Windows, all Windows.
It's been in Windows, all Windows since the beginning of time, but I figured, like other things that were useful, they must have thrown it out long since.
No, it's still there. It's never turned on by default.
Yes, well, that's, I guess, a good thing for many of us. It's not turned on by default, Dennis said. And I think that's a good thing for many of us that never use it. I remember in my youth telnetting to make airplane reservations. It worked better than calling up American Express by a goodly margin. Sabre Easy Saber
Easy Saver.
was, and they used to spell it with 2 A's because it was American Airlines. And you could telnet into their Easy Saber and make airplane reservations, and it was just ipsy-pipsy. The other thing that I would telnet into with fair regularity that the public would be aware of is Weather Underground. And strangely enough, you can still telnet into Weather Underground. So I recommend it to you.
Weather Underground? You mean? No, not the Weather Underground. Weather Underground. Well, that's what I'm trying to say. We're talking the meteorology. Oh.
Weather.
Not the Weather Underground.
This started off at a university, and it is a network of people that have internet or network-enabled weather stations. At a minimum, I think temperature, barometric pressure, and wind speed. And also, they had access to the weather forecasts of the U.S. Weather Service. So anyway, now they're a web service and a commercial business, and they provide forecasts and cool pictures of sunrises and sunsets and so on. But I think they still run their telnet servers, and you can still telnet into them. Okay, it is Sea Otter Awareness Week. There's this website I like, thedailyotter.org. They have pictures of otters and sometimes videos. So if your friends could send you cat videos, I can send your friends back otter pictures that could probably disembowel your kittens and kitty cats without any difficulty whatsoever.
For a few years, at the height of the wildcat meme popularity thing, there used to be a response to wildcats called erudite ferrets, which was significantly closer to otters than anything else.
There you go. Ferrets are still used to snake cables through difficult walls in old buildings. I think that when Princess Diana married old what's his name? Yeah, him. They had to snake a bunch of cables through the walls of the church, the cathedral, Winchester Cathedral. Was that where they were married? Anyway, some big church. So, anybody got a guess? What geeky treat outlasted the show it was promoting by over a decade? Sure. Braille was derived from what?
Night writing.
Really? I would have said Morse code. But there are smarter people here than I.
The wisdom of the law. Trust the law.
It's interesting to note that this was from the 19th century French military of Napoleon Bonaparte. How many of you might know of other innovations sponsored by Napoleon?
Canned food.
There you go. Invented by one Nicholas Appert. Not necessarily a relation, but same last name. He took peas and put them in a champagne bottle and boiled the whole bloody thing, and they lasted. And this was important to the military. So he won a prize for Napoleon for inventing this process for preserving food. It didn't involve metal cans, but it did involve champagne bottles, and the process was called canning. Important to the military because at that time, your army would march into a place, and the first thing it was meaning to do was not fighting the enemy, it was finding some food. And this would quickly make enemies of your friends, because even if you were in your own territory, your army would be pillaging the local farms, killing all the chickens, eating all the crops, and pissing everybody off. And at that point, if I'm a farmer, I'm going to stop paying taxes. And at that point, if I stop paying my taxes, there's no money to buy the bullets. Well, this is obviously a gross oversimplification, but you get the message. So that's where logistics came from. But it's very important to carry your own food so you don't piss off the farmers by stealing theirs. All right.
The actual act of canning food in metal cans came after Appert's discovery of using the champagne bottles in direct response, ironically, to the French military, because in Britain they were having similar problems with their armed forces as well, soldiers going hungry and stuff like that. So, but since they didn't have extensive quantities of glass, they decided to use metal cans instead, and that's where they got their canned foods from.
And they soldered them together with lots of lead.
Yeah,
which caused a lot of problems, especially for the Arctic explorers. I know this one. That's a T-Rex exhibit in Chicago. I saw it in person. But it's interesting, the one on display has a plastic head because the real head weighs so much they couldn't mount it with the rest of the skeleton.
Yeah.
That's the one, the guy did.
Well, they could. It would just be logistically difficult, and there would be this steel bar sticking straight up into it. Okay. Guesses?
Probably
That's interesting.
that is. Microsoft's baby.
Fastest to fly off the shelves. So I think with that, maybe we'll take a short break. Brad can hook up to the information transference device, and I can pee, and we'll all be happy.
I guess I'll wait for Kevin to return. Oh, I don't know where the actual. I see the screen. I assume we're broadcasting even. I assume we're broadcasting even.
That's the button to stop it.
No.
Sort of means that, and that was the thing that says live.
Dead giveaway that.
So that it's 50%. Yes, I saw that. That's for people that can't do 20% of dollars in their head. Well, this was a wine bar, so it may be that after a couple of bottles of wine, yeah, we're 20%. I just get smarter and smarter. I better look. I'll go get that. I'll get it.
The last time I tried it, it wasn't working. So, do not push this button that left.
Something special.
Apparently somebody can do it.
Shall we?
We should rent our phone, our radio telemetry doorbell to these other guys. Yeah, narrative well. Yeah, but it's a very attractive young lady of obvious relationship to the. One might only hope that she was there. Maybe that's just me. Anyway, it was their she was about, so I told her I couldn't let her in. She walked in like, what was I to do? I saw a shirt, some kind of sports activity, you know, some conference, volleyball or football or whatever. And the team that it was the Braves. And I thought, well, how is it that they're still allowed to call a high school team that?
Because
This day?
Braves is honorable. Redskins is the Rockets.
But still, you're not allowed to call the team Braves. It turns out this was the St. Anthony's Indian School. So I guess they're allowed. I don't know that you're not allowed. I'm sure you, if you ask enough liberals, 5 would say, no, that's not
Still
allowed.
pick that.
That's it.
What do you white people do in running the interest?
All right, so this time, hi, I'm Brad. Hey. So here for another Haiku Monthly, and as those of you who were here last time may vaguely recall, I decided to make a small investment of effort for the long term, and so I added a slideshow option to the haikus that makes it very convenient for me to go back and review the month's haikus and display them and all of that. I've made a few small modifications to it for this time around, and then I have another small one-off topical addendum that I'll add at the end. But anyhow, let's go through the month's haikus. So this is the first guy in, and apparently this is not the Ukrainian flag, shockingly enough. It is a straightforward enough haiku, but I know this simply because the next haiku in line corrects it. Perhaps someone felt slighted by the mistake, I don't know, but in any event, this is the way the Ukrainian flag apparently should look.
Mess with the folks from Ukraine.
Yes, indeed.
Getting the flag wrong would be fatal.
Indeed. So we have a checkerboard. I'm not sure what the name means. I'm sure it probably is profound. The haiku is terse. Anyhow.
It means, I'm sorry, Google isn't working where you are.
Yes. Yeah, this one's interesting if for no other reason than it seems to take a long time to load. Actually, it's that you can kind of notice clicking through the slides, it stalls out. The program, this is not the whole program. You can tell because there's no next button there, but this is just the start of the thing. But in any event, someone has taken Mario and taking him for a spin.
That's just like something that I did over 30 years ago. It's something called joystick rotation. You pick a rotation point, and the joystick had a knob, which I used for zooming. I was able to reprogram where you would get this spin. So if you twisted it clockwise, we'll let the thing go around. Oh my God.
Clearly what the haikus need are an input device. And then we have a binary clock. I'm trying to think if the time is right here. Let's see. 12, 13, something. 13 and, well, anyways, that's about right, maybe. Give or take. Okay. Oh, actually, with the clock, we should see the source code. That's not the whole source code. It's a zebra. Oh. That sort of look like a zebra. Small bit of trivia. Apparently, there is there's actually an algorithm out there that computer graphics people have found where the shape of a zebra's stripes is actually something that you can compute. What it ends up being is that if you take the shape of the zebra fetus and then extrapolate that out to the full-grown zebra, there's an interference pattern that is what actually generates the difference. So there's a set of cells that are all sort of uniformly distributed in the fetus and then expanded out. Anyhow. A breathing spiral. I think we've had a breathing spiral before, but we have it again.
Don't exhale. That's exhaling with a pause.
Yeah. Okay. Oh, and we need the redux because, you know. Okay, then. Whoa. There we go. Somebody's fixing it. That's more like breathing. And because spinning Mario is not enough on its own, we need to spin around something. And it spins. And of course. We have the flag of Vietnam and Vietnam Gold Star. Actually, I want to go back. Oh yeah, this is the whole haiku here. Very nice. More. And thing. And a red ball, albus, and it is a red ball, and a boring gray ball.
It's not boring at all.
Now, my wife, you know, took a look at this, and her observation was that isn't the inner circle usually a little thinner? Ah, okay. And of course,
So Republican Korea is probably
Republic of China.
okay.
And actually, I was going to ask you. So this is the KMD's flag.
This is what Dr. Sanya said.
Ah.
He had designed for the KMT.
Mhm. Mhm.
That was in the turnout. I think in the year 1990.
Mhm.
So the idea was it's a sun
Mhm.
with rays shining.
Is there significance to the number of points in the?
Yeah. In the center, it's the sun. With the lights shining from the sun in the blue sky.
Eight colors. Aha. It's the modding. Yes. And ooh, yes. And that's the whole thing. Yeah.
I think there's another guy who did the nanograph, but I just took his code and put the color.
And then, oh, here you're varying the coloring scheme.
Yeah, it's some kind of graphical user interface. All the colors.
Yes, yes. I remember, yeah, that was,
You're very aesthetically appealing efforts years ago.
yeah, I think now
Oh, is this-
it's possible that you can use a joystick or using mouse to try to reach
Oh, this is a more continuous variation than the still quite terse. Is this Sam again?
the same chain. He's improving on the shading.
Yeah. Ah, and how the boring gray ball, but with varying lighting. Also similarly terse. Well, this is the whole shader. I mean, what shading function is probably something like a Lambert shading or something. I don't know.
All I remember from 35 years ago was
Long, yes, indeed. Flag of China. Very nice. I'm impressed with Ping stars, but he's going to talk about those. So I'm not gonna... Ah, intriguing. Also, quite compact.
Now what we do, not recognize the flags, we recognize the countries. Bartuda.
Huh. Wait, I'm noticing a theme here. Aha. Wonder why star and... Is that it?
Draw a star, you can draw a lot more flags.
I bet. I wonder if there's a significance to the moon and star. Is there some?
It's the Islam.
Okay, but
Islam's
oh, really? Both the star and the moon.
star.
Okay. Oh, interesting.
Oh, you would face that. Yeah, a lot of green crescent, what you see in the morning.
Huh. Interesting. Oh, very nice.
Where's the swastika? All right.
Oh, this one looks a little more involved.
Nice.
It looks like Chicago.
Huh.
Actually, the flag of India, it has the center of the sun, and it has a human figure
Oh,
facing
is there?
like
What's with the redux here? There's two versions. Is there?
I
Which one?
One version had the color was wrong.
Ah. Okay. Yeah. What's this now? Huh. Oh, not very much code either.
Just haven't expanded.
You're doing more levels, or?
Yes, more levels.
Oops. Ah, very compact. Very clever. And so Ting pinged me midway through the week. He was having trouble duplicating the stars, and I'm sure he'll talk about the details of this later. But and of course, I botched the number of stars after having figured out how to double it up. Realized it shortly thereafter. There you go. Yeah. So.
Success in approximation.
Yep. And what was Sam trying to vary here, I wonder?
He just couldn't walk.
Oh, more of them. Uh-huh. Ah, and even more. Comments in Chinese. Ah. Moon Festival. Actually, we should go back. That one's probably quite sure.
Sunday is the Moon Festival.
Ah. Short but sweet.
By the way, Lord God is running something really special, and he arranged to do this around the sequence of lunar eclipses. So this is it. Borrowed. That's how God is.
This is a name I haven't seen before here. Camille Vanderhooven. And it's very short and in all caps, no less. That's certainly interesting. Someone has had a little bit of fun with the American flag. Cube from a star.
That's for the end of the movie, the president's analyst.
What's going on here, Ting?
Well, I'm just trying to draw lots of cubes. So
Huh.
this is just one of it.
Oh, I see.
It is actually a star. It's, 6 sided.
Ah.
Because the line makes it a cube.
Yeah, just by the coloring,
Yeah.
illusion of a cube.
Huh.
It's just really 3 dimensions.
Hmm.
Yeah.
Ah.
Now you will vote Democrat. Now you will vote.
We live in
Now you will vote
California.
Republican.
It doesn't matter if you live in California.
Don't know why that one's different. Ooh, because if we can make one thing wave, we can make all of them wave. I'm assuming it looks like, oh, he's done what I have often suggested folks can do, is just you can tack something on the front or the back to mutate the haiku. So he's warped the coordinate space up front here, and then that has it, and then he's able to put that in front of other stuff. Yeah, very typically, if you want to, in general, if you want to warp the coordinate space, you want to do that in front. And if you want to warp the color space, you want to do that at the end after you've got everything afterwards. So, and of course, warping one thing isn't good enough. So, and there's that same pattern up front. Ooh. Oh, wow, that's really... Don't stare in the middle of that one. Jeez.
You know how Google sometimes comes up with login, so we know you're over.
Okay.
You need a login and make sure that you tell us that you're not hungover or subject to epileptic form seizure disorder.
Hmm? Oh. It's built into the clicker, but
Might not be showing on the red screen.
okay. Well, I'll have to two-hand it. Yeah. Anyways, woo, that is quite a one. Okay. And we have a surface of, whoa, multi-views. That's pretty trippy.
This Chinese firm that's selling a pointer that they call the burning laser.
Okay, we have a sine wave.
Or the screen starts to smaller.
Yeah.
Yeah, that's
Indeed.
another problem that Thailand.
Huh? Yeah. You've been hearing much from them generally? They post their haikus, at least. We can thank them for that. Ah, here's your cubes.
My goal.
Okay. That is really weird because I see yellow.
Yeah, on the edges. What is this thing?
Yes.
Oh, that's interesting.
Is that an artifact or is that not really?
It's just mismatch.
Oh, it's like an overlay.
Huh.
I think it's
Red is, yeah, it's red and green.
just that
Yellow.
defect that vacuum get all the numbers.
Right.
Wind tunnel.
Looks like the Imperial targeting.
Star Wars.
Ah, and now we get the colors.
This must have been hard to do.
Yeah. Aha. Well, it's at least it's well commented code, right? And we got Hongsa. Ah.
And this is a platform for kids to
Yeah.
learn how to use numbers.
Lance, maybe? Hongsa. So he's got each piece. Hongsa. Don't know that one. Wow. Black.
Just a small kid who can look back.
Yeah. 0.5.
Still pretty impressive.
Huh.
All right.
X0.
The code. Yeah, it's just using comments.
You get this, fly this kid in to do the introduction to haiku talk.
Okay, this one seems to have croaked for some reason, but I'm guessing something. Ah, and then we get people complaining about the because we have an active community and the varying levels of skill apparently amongst our users. Hmm.
So was this a comment on
Someone posted this. One of our avid users here posted.
MS Paint for it?
He's not supporting the community of folks learning here. Let's see. This one mystifies me. So it's, oh, I see, each direction. Oh, battery. Don't stare. Oh, okay, I'm overusing this. So much for that.
Deleting inactive haiku or just
So I have a general.
everything online all the time forever.
So I have a general issue with how to cope with the ones that are sort of accumulated. I mean, at any given time, you see the ones that have come in recently, and then you see ones that have been upvoted, but it's not a very good way to get visibility into what exists. And so I'm. Ting had a good suggestion earlier. We were actually just talking about this topic of maybe if I had an index where I show the names, because one of the issues is if I display a page full of a ton of them, I'm not able to, well, okay, that's not going to help much the names with these, but in general, if I display all of the images, it will bring the page to a crawl. I can only display so many of them on a page, unfortunately. What I could do maybe is pre-compute on the server and store a snapshot of what they look like, and then I could bring up a bunch of them. But then I'd have to do work on the server. That would be tricky. So a number like this where they're learning various things and step by step.
Well, you could build a thing like the SETI screensaver that goes out and gets all the clients pre-compute these things and send it back.
It's not a bad thought, actually.
Yes, it is a bad.
We got various,
Looks sort of black and white Amiga-ish.
lots of more patterns, people learning the ropes of the operations. All kinds of fun.
It's starting to get.
And now here, let's see if I'm going to try. So this one is designed to go with audio. So let me see if this works. Oh, that's not going to work, of course. Let's see. Oh, I know why it's not working. Still not working.
Yeah, again, you could probably design something to give someone with epilepsy serious problems.
So this is switch problem.
So this is the first time that you've actually had anything musical.
Yes, someone has actually figured out how. If you'll notice, there's actually some melody in there, and if you look at they've actually been thinking. Right, they were thinking through how to get particular notes.
Definitely a switch problem.
Thank you.
If they wore is 5 years old, that should be
It's a different one.
This is very nice.
Good. My little trick to do. I only have 3 buttons that work, so I had to use double click, and I was not sure why it wasn't working when the volume wasn't turned up. Anyhow, wavelengths from the same F-Nord fellow. And thank you out there, F-Nord, wherever you are. I'm impressed to see someone actually successfully did something musical with that. I confess I largely failed. Event horizon. Ooh. Very terse as well. Oh, I should look at the code for this one. These are all nice and small. And continuous plasmoid, I'm not sure what the difference is, but. Doesn't really do, the screen doesn't do it justice, but there's little sort of quivering. Intriguing. Ooh. Huh. That does sort of look, and not much to it. It's very small too. Doesn't take much to trick the mind. Acid peacock, okay. NBC. Also very small. Oh, I can see it. That's pretty neat. Yeah. Definitely see the spider. Also quite small. That's sort of like eyes. It's also quite small. That's you. That's neat. Yeah. Oh yes, and this is the one I was mentioning to Ting earlier. So clearly we've had a little bit of inspiration from the use of ideographs, because if you'll notice, this fellow has very carefully gone and defined a bunch of very small single Unicode symbol operators, so that he's able to define in terms of half circles, and he's got a square root, and the up arrow is an R push, and the down arrow is an R pop, and He's combining it in clever ways.
This is a program in Chinese. All you have to do is use Chinese for words. Use Chinese word to define the words. You can write the whole thing in Chinese.
Yeah.
All right.
You got Batman. And
3D.
3D. Woo. Ooh. It's a little more distinct there, maybe.
Yeah, this is just the color gradation.
Huh.
Okay, the same pattern. You just change the coloring.
Ah.
And it looks like a light. Yeah.
Huh. I feel like he raised that one vertically as well.
That change is you change the color table.
Ah. This one goes more slowly, it looks like. Something. Huh. Ooh. Boom. Uh-huh. And what does it say?
Sine wave.
Sine wave, okay. Aha.
Good guess.
Aha. More slow moving dances. Quite small.
It says seasick.
Seasick, indeed. And seasick redux. Huh. Yeah, staring at that's not doing me good things. Okay. And more variations. It's kind of neat, though. The inner one has this sort of nicely shaded. And we're back around. All right, so then, anyways, I want to briefly talk about something that I'm not going to be deploying to 4th Haiku in the near future. I'm going to go to a different page here. So something that folks have asked me a number of times, and I've sort of never had a good clear answer. Oh, and by the way, thank you, all the haikuers out there. This is all the other folks' work, and I'm very grateful for folks who submit haikus. So something that a number of folks have asked me over the years actually is what about 3D? So the trouble is, and I'm going to grab a whiteboard marker. Yeah, well, so there's a number of issues, but the biggest one is sort of what would 3D mean? So conventional haiku, you've got X going from 0 to 1, and you've got Y going from 0 to 1. And oops, 1. But the trouble is, what could I do for 3-dimensional stuff? And different folks have proposed different things to me over the years. The actual hardware thinks in terms of sort of 2 stages. There's a what's usually called a vertex shader, where you take some piece of geometry, do something to warp it, and then on top of that geometry, you render a fragment shader, which is actually what all of these are. So you've got some description of what's on the surface, and then you mutate that. But another suggestion that folks have made to me quite frequently is what about voxels, or actually having pixels in 3-dimensional space? And what that would mean is that you would need to have that line going out of here and have Z. And so for the longest time, what's kept me from doing that is that it's sort of an instinct that it might not be very performant, one. And then another concern is displaying voxels and having them actually look like anything is actually relatively non-trivial. But I thought, enough people have suggested it that I should at least play around with it a little bit. And I found a little bit of time and was able to do a small experiment, which I'll show you all in a moment. But basically what I did, I made a couple of changes just because of, I had some assumptions in my head about what what would be convenient, especially if you were thinking in 3D. And one of them is that I was concerned that a lot of the sort of easy objects I could imagine making were like spheres and things. And so having a coordinate system where I'm just going from 0 to 1 seemed inconvenient. So I decided to temporarily put things in a mode where I've got, where I actually draw from -1 to 1, and from 1 to -1 in X and Y, and then the same thing in Z, so that I got something symmetric. And then the other issue is how to actually display that on the graphics hardware, because one of the things I definitely wanted to be able to do is to do it fast enough to have time as a component as well. And so what I've done in this experiment is actually one of the more rudimentary ways of displaying voxels, which is, if you can imagine, so the usual haiku, what's actually being done is that you have the screen and you're just drawing, I'm actually just drawing 2 triangles on it, which is what the hardware actually knows how to draw. And so that's fine for the flat haiku. What I do to render a voxel image, a 3D cube of space, is I, in perspective, draw a succession of sheets at different Z depths going forward and stack them. Now, a huge issue with this, well, there's a number of issues with this. One of them is, of course, I'm cutting off the coordinate space by doing this, so I'm sort of excluding anything outside of a certain region. That's one issue. Another issue is that if I just had a static mapping of this, it wouldn't be very interesting. And so one of the things that I did, just so you can see what's going on here, is I have a camera that just wiggles back and forth so you get some sense of what you're actually seeing in the two-dimensional space, or in the three-dimensional space. And then the really fundamental issue is that, and this is the problem with all voxel drawing, is that we don't actually, we see 2D images. We don't actually have the ability to see through an object. And so much like viewing an X-ray, you have the problem of what you actually show. And I've just gone ahead and done the very simplest thing, which is, I believe has some correspondence actually to what an X-ray does, which is you're just seeing the accumulated density down through in with each of the primaries. Now, if I wanted to do something nicer, what I might be able to do is something where you imagine casting a ray in and actually treating it like a material and having some reflectance. Because when we see objects in space, what we're accustomed to actually seeing is, I see the light coming in, but really it's light that's been bounced from all over the place. Whereas in this way of seeing things, it's, if you can imagine a semi-translucent sphere of gel, seeing just light passing straight through. Which is not a very compelling effect, as you'll see. There are some interesting things about it, though. So the other issue, of course, is that by having a finite number of these slices, the fidelity in Z is actually very limited. I've just gone ahead and done 64 slices in Z. It's not as bad as you might expect from that. 64 is enough that you can get some amount of blending between the layers. It also helps that because I'm doing this just an accumulation stacking function, that the layers actually tend to blend fairly smoothly. The other issue is that you'll notice I mentioned that with this camera I'm only wiggling side to side, and the reason is that if you actually want to have slices that transect in different directions, you very rapidly get into uncomfortable places in terms of how you have to present the images underneath. So I realized later, I haven't done this in this version of it, but what I probably could have done, since I know rather than limiting myself to these regions, since I'm really interested in visualizing an entire 3D field, I could have filled the entire viewport at each of these layers and extended out beyond for the layers that are further back. That would have introduced other issues, and I might still at some point play with that, but I happen to have not done that. The problem is that even if I did that in X and Y, which would give the illusion of an infinite field in X and Y, the problem is that in Z I have a finite number of layers that I'm willing to draw. And so you're definitely getting this sort of you know, visual channel there. The other thing that some folks do that I played around with but didn't like the result of is a different middle ground. So you know, the ideal thing one might do is you'd be specifying the material at each location, cast array in, and do actual interreflection. That's incredibly expensive to do correctly. A sort of one step up from just accumulating the color with stacked blending is that you could stack layers where things in front overlay things in back depending on their opacity. I played around with this a little bit, and the problem that I ran into is that typically if you do this, then you actually are you're obscuring what's behind, which can be good if the goal is to say, imagine, you know, describe a sphere and getting something that actually looks like a sphere. The trouble is, because you have no reflectance property on the surface of it, you don't actually you end up with flatly shaded objects. Now, possible embellishments are, if I knew the normal at each point, I could apply some simple shading function and decide what to do at each layer with that shading function. But of course, then I would need one more piece of information that I don't actually currently have from the haiku, which is only giving me a color value. So I don't actually have a shading function. I could do something like, you know, take the gradient of it and try to assume that that somehow represents the surface, but that might not be a terribly good assumption. Or I could take particularly the gradient of the alpha value. And I should mention, actually, by the way, when I'm stacking these layers, I'm doing RGB, but for all of these haikus, I'm assuming I need to stack the alpha value, or else it isn't very useful. If everything is, if you imagine each of these squares being completely opaque, you're only going to see the outermost square if you stack them in that way. So anyhow, let me go give this a whirl and show. And the thing is, part of why I haven't deployed this is, of course, this is, you know, woefully incompatible with the existing corpus of stuff. I'm using a feature of App Engine that lets you deploy a different version of the software at a different version number that isn't pushed live. And so I'm able to, you know, display all of the existing haikus under this new pattern. But let me start with just from scratch here. Ooh. And so I'm going to scale this up a little so we can see things better. So if you imagine here, I'm going to just start with a, let's say with an orange, solid orange. Well, that just looks solid orange. There's nothing particularly interesting there. But for RG and B. But if you imagine then that I take the X coordinate and I'm going to take the absolute value of it and then clip to where I'm less than 1. So I'm going to stay within the unit value in X. And the same thing in Y, and the same thing in Z, and then I'm going to multiply those together. Then I get something like this. So now you can see sort of carved out in that space, the cube. And then what makes it more, but of course, because the alpha value is 1 for all of these, we're not getting something terribly interesting. So instead, I'm going to multiply that last piece by 0.1. And now we can sort of see, that's not showing very well on this display. Let me pick a different color just to get, there we go. Just a little bit. And so now you can sort of see the accumulation as you go back. So imagine sort of a solid cube of Jell-O or something as you wiggle from side to side. What's that? Like which? What is aerogel? Okay, I'm intrigued. Aerogel. What's the name? Aerogel. There we go. Wow, that's frightening.
Remember the thing where the space probe that was trying to capture stardust? That's what they use.
Huh.
Right there. That's the thing right there.
Intriguing. I have learned something new. Thank you.
Yeah. In fact, like I said, if you can get a really dense gas, you can put a block of aerogel in there and it'll float on the dense gas.
So you can imagine doing some interesting things with this now, because you're now visualizing this sort of cubes. So the simplest thing you could probably do is take, you know, X, Y, and Z for RGB, and then you get sort of the RGB cube. They're accumulated. Although actually, you'll notice it's got kind of a gap in the corner because it's, remember, it's going from -1 to 1. Something more interesting, let's say we mix in time a little bit. I don't know, something like that. You can sort of do things in the interior space of the cube. You could imagine varying the space of the envelope, let's say over time. Oops, no, like. Oh, that didn't do what I thought it should. Oh, that's too short of an interval. Let's do something else. Let's do, so if you accumulate you can do a sphere, which is hard to see because again, I did that higher opacity. If we make it more translucent, then we can see into this, nope, not that translucent. You can see into the sphere. Let's see, we could mix time in a little bit. Oops. Oh, that's making it bob side to side, right? Because we want. Whoa. And you'll notice, actually, it's not as visible on this display, but you can see the banding between the layers a little bit there. So anyways, there's some interesting things here. I definitely, I haven't completely abandoned this. You'll notice that I'm using a different laptop than I normally use, and there's a very specific reason for this. This is a Chromebook Pixel, which I previously had not assumed had that great of a graphics card, but apparently has a far better graphics card than that Mac. And the reason is that, unfortunately, because this is drawing 64 slices, it's somewhat, you know, less performant than, you know, it's not quite 64 times as slow as the normal haiku drawing, but it gets up there. And so this is dramatically more computationally expensive than the usual haiku whatnot. So one of my hesitations in deploying this more widely is obviously that. The other is that, you know, the translucent thing isn't doing much for me. But let's take now an interesting thing to take a look at is imagine some of the existing haikus. Like, let's take a look at Pac-Man. So as I should have said, that the Mac that I usually use works fine at the smaller resolution, but if I blow it up to anything larger, it actually hangs the machine. So I don't recommend that. Let's see, size. Actually, no, I want to do create derived work and then do size equals 500. So here's Pac-Man, and you'll notice that he's up to the upper right quadrant because of the change of coordinate system. But now let's say I do a couple of things here. I can make him translucent, and now we can actually sort of see that slicing happening. And then I'm going to actually, let me change the coordinate system so we can look a little more closely at him. So I'm zooming in on the coordinate system. And you can see sort of there the layers stacked on top of each other. Let's take a look at another. So in general with this, I'm in some ways I'm encouraged and in some ways I'm discouraged. I'm encouraged that the layers blend as nicely as they do. Here's that running man stacked in the actually, you know, that gives you a chance to really see the you can really see the layers here because he's got kind of a, you can see the aliasing artifacts because it's got a more sharp boundary. This one's doing terrible things even on this machine, so I'm going to kill it before it does worse things. Pong is actually an interesting one in this space because, of course, it actually, you can sort of see what's going on here. Even more so if you give it a little transparency, then you can kind of see the X-ray view of what's going on. You can imagine, let's say, Z abs 1 less times. You could clip it to a narrower paddle, that sort of thing. Use a random number. You mean? Well, I'm getting the Z component as an input. You mean clip it by a? Yeah. So I could do like this because it's random per pixel. So then, yeah. Let's see. You could imagine doing something X and Y. Let's say in time variant. Oops, that didn't quite. Let's see. Oh, that's too much. There we go. And sort of got things feeding through that. You could imagine doing. Let's see, X times rot, Y times rot, Z times rot. Give it coloration based on its position. But the thing that's sort of striking to me is how it, in some ways, is not any. It isn't dramatically more flexible than the 2D ones in some ways. I do think that having materials may make a difference if I'm actually trying to do something where there's reflectance at each point. Getting that 3D shading for free might make it easier to do real solids. If you can imagine, ideally, that haiku I showed, with a cube or a sphere, if I got correct shading sort of implicitly from the surface, that would be fairly significant. But so anyways, this is a work in progress. Please, feedback welcome. I don't have any clear plan for how I might be able to deploy it because unfortunately it runs dreadfully slowly other than on fairly fast machines, and even there it's fairly easy to get it into a place where it hangs.
You understand the real problem you're having. 2D, all you're doing is just writing it in your viewport.
Yes.
When you do 3D, you've got really two coordinate systems. You have the world coordinate system where you put your objects in.
Mm-hmm.
Then you have your camera
Yes.
coordinate system, which now in the world coordinate system is a right-handed. The camera is a left-handed, meaning you have X, Y, but Z goes towards the pointing at.
Right.
And there, you also, if you think of it, it's like a pyramid. You look at it, because what you have to do is you have to clip things that are not in the scene, and you also have to clip in the X and Y. You can't, just for implementation's sake, things that are too far away, you say, well, I'm not going to show those. And you also have to have the near plane between the scene and the camera. That's the other one. So that's where you have the real computationally intensive. That's on your viewport. That's where the x86 architecture, how they have SSE instructions.
Yeah.
And it's like it's a matrix multiplier. Really what it is.
Yeah. No, a lot of this is hitting things that are not cheap to compute. It's definitely every little bit of performance matters here.
If you go through the math, you might be able to say, oh, if I make this assumption. You know, because like you said, all you're doing here is you're just moving in X.
Mhm.
You're just actually rotating. If you think about it.
Mm-hmm.
And it's like what I did with George Stickler rotation. You know, calculating sines and cosines.
Mm-hmm.
I just used the polynomial expansion.
Mm-hmm.
It worked like a charm.
Yeah, no, it's
All my things, and yeah, I helped out a little bit. You know, it took me a hell of a long time. Oh, and get this, I had to do it in assembly language. I had to do it for 6800.
yikes.
Remember, I also was driving a graphics.
Yeah.
But yeah, they did like it a lot.
Yeah, no, it's tricky. I mean, it's sort of you want to be able to to really get something performant. You oftentimes need to dive down to a low level, and the frustrating thing here is, especially with the haikus, I'm trying to make it as general as possible, and so the trouble is that it's when I can try to optimize, but at the same time, I'm trying to let people, sort of throw random things at me and see what they do with it. And so, in the same vein, I had to for the 2D ones, I actually have a cap on how many operations they can do, so that they don't overload the capacity of a typical machine.
And now the nice thing about doing 3D graphics, you can change things in your world coordinate system to show things moving around. Plus, you have the ability to move your camera.
Mm-hmm. Although actually that raises one interesting frustration I have with this as it currently stands, is that while it's freeing obviously to have the camera independent of the world, the trouble is, but now how do I specify the camera, right? I have baked in a camera that bobs side to side, but that's not necessarily the right thing for every haiku. Mm-hmm.
Because that's the whole idea. You go, well, what's going to be dynamic? Is it going to be the camera?
Mm-hmm.
Coordinate system is dynamic, or are you going to have things in your world coordinate
Right.
system move around?
Right. Yeah, no, I could certainly, you could imagine, like with Pong, if I had just frozen the camera at one spot, it would have certainly, it simplifies the model, but then, this is only even remotely interesting because the camera is moving, and the camera moving is sort of an easy thing to specify globally. Whereas, imagine if I were warping the world, to match an imaginary camera, the number of lines in the haiku to even express that would be quite huge. Yeah. 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 Yeah.
Usually the smart thing is don't have your world coordinate system on LSD, not your camera.
Yeah.
So, in any case, that's a very computationally intensive system.
Mm. Yeah, no, intriguingly, I have some long-standing history with voxel rendering. I actually worked with a guy when I was an undergrad who was visualizing these data sets of the visible human, which is this data set where they took photos, slicing through the layers of a corpse of a dead convict. And one of the issues is he was actually doing ray casting, this is way back on old parallel SGI machines, and he was doing ray casting into the data set, but he had to make a lot of very broad simplifying assumptions to make this work. He had to make the data set 8-bit. He had to split this up over 8 different or 16 different CPUs. And then the irony was that he produced this for a demo for SGI to use. And they're like, this is terrible. You got this demo for us, and it's all CPU computation. We want GPU stuff if it's doing voxel rendering. And huh? Uh-huh.
I do remember that it was for medical
Mm-hmm.
parts of the human.
Yeah, yeah. I imagine in general this is an area where there's sort of 2 ways you could take it, right? You could, in the medical case, right, you've actually got a data set where you're interested in what's inside, and
in some sense, you actually want a way to display it that helps to highlight what's inside because you're trying to see it. And I'm unsure where to go with this. Like, one option is to go that direction and try to highlight the interior space, whereas the other extreme is I could say, okay, well, I'm just using this as a mathematical way to express a shape, and then I want to render with normal sort of surface into reflection, but that's a different direction. Then that would be a terrible way to view an X-ray, but it would be a fine way to visualize, sort of a cross-sectional view of the exterior of an object. So, anyways, it's definitely. I don't have good answers for this, and that's probably why for now this will stay an experiment. But any thoughts about how to make this more substantive? I'll probably. It took me a while to realize afterwards that, I don't actually have to, if I'm going to draw a polygon, I might as well draw one that fills the viewport at each layer. So, anyhow. Cool. Any questions?
Okay, got the sound? Okay, there it is. Okay, what I'm talking about the stars. Okay, and let me see. The problem is to draw a star. Everybody knows, or the kids knows. You take take anything. You see it when you bring up kids. You see all these things on the wall. Everybody knows how to draw a star, but to specify exactly mathematically what the star is, that's kind of hard. So I think a couple of months ago, I showed you that the way I thought, okay, if I want to draw a star, I first draw the sawtooth. And if I wrap the sawtooth around in a circle, then I should get stars. But it doesn't work that way because the sawtooth, it's a straight line horizontally in the x-axis. But if you wrap that thing around into a circle, the lines get distorted. And so I got daisy instead of star. I think 2 months ago when we have these 2 young kids coming around, I was talking to them and I said, well, I really have to specify exactly what a star is in order to be able to draw it correctly. And any other way would just not work. Okay, how to specify a star? Generally, if you have, we can use a polygon. So you specify points, and you just draw the connecting the points. And then you can specify an arbitrary shape. And if you want it, it can be a star. But you have a list of points, and you connect them with straight lines, and that's a star, of course. But when you draw a star, you have to decide whether you are inside the star or outside the star. And that's logically quite difficult because you get all the lines and you have to decide, well, am I on the inside or am I outside? And so this, generally mathematically it is plausible, but it's kind of hard to realize in a drawing program. So here, I thought that the exact and complete specification of a star should have these parts. First, you have a circle where you are containing the star. So to specify the circle, you need the center and the radius. And then you have to specify how many spikes you want to have this star. And then you have to decide the angle of the spikes. Okay. And then another thing which I realized later was that you have to specify the offset of it, because the star you put on the screen generally is on the wrong angle, and you have to correct that. So with these things, with these parameters, you can draw arbitrary any star or any regularly shaped star. And so how do you specify the parameters? And these are the parameters that you have to have. Okay, when you draw a star, basically you have to decide you have the side or the sides on the spike. And if you have a point here, this point, if you can compute the length of this line, and then if the point, the XY point, has a distance to the center less than b, then you are inside of the star. Okay, so basically you want to specify a triangle there and compute the length of b. So here, how to compute the length of b. Okay. And this one, we go back to the these are the list of parameters. Of course, point to be appended, x, y. This is this variable in the system. You don't have to specify. It runs automatically. X runs from 0 to 1, Y runs from 0 to 1. And then you have to specify X0 and Y0. That's the center of the star. And what you want to compute is the distance from XY to X0 and Y0. And then the angle of XY, this point, from a reference angle. Generally, it is horizontal line. And this I call theta. And then from theta, you want to compute the angle from the nearest spike, because that's the small angle that you need to work at. So from theta, you need to compute the beta. And alpha is the angle, the half angle you have as a parameter. So this I call alpha. And the triangle on the alpha side, it's called A. On the beta side, it's called B. And then the height of the triangle is an H. So let me go back to this. Go back. Okay, there. So here it is this triangle. That's what we want to solve. You have the alpha there. That's the half angle. And you have the theta there from a reference line. And you have to compute the beta, which is the how far this line deviates from the center line of the spike. So the R is the radius of the circle, and A, B are the other two sides of the triangle. So you have the alpha and beta and R. You have to try to solve for B. And then that's just a simple geometry or trigonometry. And basically the edge, the height of the triangle, it is A times sine alpha, or it is also equal to B times sine beta. And the R will be the sum of the two sides of the two subtriangles, and that's A times cosine alpha, B times cosine beta. So you have these two equations, and you can solve for B, okay? And B comes out as R times sine alpha divided by sine alpha times cosine beta plus cosine alpha times sine beta. So it's looks complicated, but it's quite easy to express in haiku, okay? Because sine and cosine, these are all functions that's readily available. And once you compute B, and the simple condition of a star is R less than B. So well, I didn't show the code, okay? But the code is kind of complicated because I want to put all 6 parameters on the top of a stack. And once you have all 6 parameters on top of the stack, you can just grab one parameter at a time and eat all these 6 parameters, and you get yourself the B. And if you just put down the B less than R less than B, you get a star. Okay, so this is 1 star, which is 5 spikes. And if you, because the spikes is a parameter, you can spice any number of it. and you have a sun with the 12 spikes. And this is looks like a 6 spike star, but actually you need to break it down into 2 triangles and overlap put the 2, turn one 180 degrees and superpose of them, and you get this Star of David. Okay. A triangle, it is easy to specify. It is a star with 3 spikes, and the angle is 60 degrees or 30 degrees. The half angle alpha is 30 degrees. And then you get a straight line instead of a spike. So once you can draw 1 star, you can do all these things quite easily. And put 5 stars on. It's a piece of cake. That's hard. And I ask Brad, I need 4 next. I need loop. And I couldn't do it without a loop. And finally, Brad did it with mod. Okay, mod is just mathematically it is a loop. Okay, just divide it by any number, and then you can repeat it as many times as you wish. Okay, now then what I want to do is to do a screen full of these hexagons. Okay, if you paint the hexagon in 3 diamonds with different colors, you get the illusion of a cube. Okay, so this is I need to draw a star 6-sided hexagon, but that's a 6 spike star. The only thing is that this angle is 60 degrees, and so the 2 sides line up into a straight line, and that you get a cube instead of a star. And then you can specify, because this angle, you can use the alpha to decide which color to use to paint. And if you have 1 star, well, you can have 120 cubes. These are actually 120 stars, and each star is hexagonal. I couldn't, well, if I spend more time on it, I couldn't adjust the radius and then the position of the stars to get rid of the overlap. But I think it's good enough. Okay. Questions?
Where do I put the star?
Yes.
Okay, so it's, you say move here, draw star. Move here, draw star.
Yeah.
Okay.
That's right. I think all you have to do is to specify x0 and y0 to position the star.
Okay.
And Brad said that, well, if you do the x, y, you do the use a slash mod to divide them into modulus.
All right, now, it looks like you had to do what's called area fill.
Yes.
Okay, because I remember that was the last thing I did when I was at Calcom. And basically, the way I check it, I'm trying to remember, this is a long time ago, is you pick a point inside the area fill, and then you have these list of vertices. I think you add up the dot product
Mhm.
of the vertices.
Mm-hmm.
If it's 0, then you know you're within.
Mm,
I think that's what
this is hard. I think this is the hard part. Yeah, this is hard part to do the fill. That's the how do you do the fill?
Yeah, because this was already in hardware. So
Mhm.
once I said, okay, yeah, this point is within the thing.
Yeah.
Then I tell the graphics engine to fill this.
Yes. Fill is a common
Yes.
common function
Yes.
in a graphic package. When you draw a shape, you can specify what color you filled it. You can just draw the edges. You can specify the color of the edge and then the color of the fill.
Yes, that's like with Brad. When you do 3D,
Yeah, but Brad didn't give you a fill function.
right.
Okay.
The shape of a plane depends on what the
Yes.
the angle of the
Uh-huh.
normal,
Uh-huh.
the angle of the camera.
Yeah.
It's the axis, and then you get some.
Yeah.
And trust
Yeah.
me, it was
Mm-hmm.
back in 1980.
Yeah.
when I did this.
Yeah, you see here, with a fill function, then you can do it this way. You can specify star the easy way or logically the easy way. You just specify the a polygon, and you'd say fill, and yeah, yes, but then when you are drawing without the fill function, this is the fill. Okay. Yeah, right. Uh-huh. Yeah. Yeah. Okay. Any comments? Thank you very much.
Let's see if the second floor head is still open.
I think the second floor men's room is still open. There was one thing I wanted to include in our new stuff, and that was the iPhone 6.5S, whatever, that just came out. Up half-ass, yes, exactly. Thank you. Thank you for seeing through my thinly veiled subterfuge. But anyway, the iFixit folks have a teardown of this brand new thing, and I think they had it on the air before it even existed. And the way they did this is they got in an airplane and they flew back in time to Australia, to where there actually existed this brand new product, and took it apart and sent the information forward in time to us here in the real world. This indicating Australia, even though are they ahead or behind? It's hard to tell. Anyway, so they actually flew there, and they were not the only ones, apparently. There are some folks that do this routinely with every new thing that is released elsewhere. I guess there are Harry Potter books that people used to buy in England because you could get them faster than if you bought them here. And so it goes. So with that, we'll take a short break. What a relief it was.
Am I on? Audio check. Audio check. 1, 2. All right. So my name is Sam Falvo, as you probably are already aware, based on the evidence that I'm presenting on the Kestrel. This Kestrel update is a little bit different from previous Kestrel updates in the sense that I have absolutely no preparation whatsoever this time at all, except to say that I'm going to be speaking about that little guy right there, which, there we go, which is this guy right here, the BSPL compiler. So, hey, it even kept my font size. That's good. So, long story short, many months ago, I did a kind of analysis of machine forth compilers, especially since I used one for the Kestrel 2 to write a number of small applications and also its operating system in. And the techniques for compilation that I used on the MISC processor were sufficiently simple that it kind of hid, well, what's the word that I'm looking for? I kind of got used to the simplicity of using a MISC architecture, and the compiler for that was very straightforward to write. The problem is when I looked at the equivalent straightforward code of way of generating code for a RISC architecture using machine forth, it came out really, really bad. Not that the code didn't work. It's just that it required extreme, very large numbers of instructions to get something as simple as addition to work. Because the RISC is so atomic, unlike most CISC machines, that all your individual steps of fetching from memory and updating registers and pointers and things, all of these have to be written out as separate instructions, and these instructions are all 4 bytes long. So a simple addition could easily take up 12 to 16 bytes, depending on how you do things. So here's an example of what I mean by that. So this is if we keep our stack in memory with no top of stack caching, we find that simply adding 2 numbers takes up 5 instructions. That's 20 bytes a pop. If we do manage to cache the top of stack in a register, it's a little bit better. 3 instructions. That's now down to 12 bytes. That's still a fair bit, and it still takes a while for information to be processed. I apologize if I seem kind of stuttery today. Like I said, I'm completely unprepared due to life, work, and stuff. So why CISC processors are a good target for MISC or for machine forth? Well, this example from the 68000 is a good illustration. 2 bytes to express that instruction, maybe 8 clock cycles if you're lucky. So a 68000 definitely is a very good architecture if you want to write a machine forth compiler for. 80x86, obviously we have historical proof that machine forth does work on it because color forth is written in that way. It's not as good as a 68000, but it's still pretty good. I mean, a 1 kilobyte kernel with a decent compiler included, clearly there's proof in existence, proof that it's a pretty good target for machine forth. So what do I do now that has changed my mind with respect to RISC architectures? Why am I now saying that yes, I can have a machine forth compiler for RISC? And there are several fundamental shifts in thinking that you have to go through in order to really come to this conclusion. I think the first thing that hit me was maybe I shouldn't just stick with a 2-stack architecture. Maybe instead I should use 3 stacks. Keeping the data and the return stack in memory is valuable, obviously, for passing parameters back and forth, and also obviously for subroutine recursion and such. But the actual evaluation of information during the flow of a program's control flow is probably better modeled using an independent stack, which we can map the CPU registers to. Because otherwise, with the conflation of the data stack with an evaluation stack, we end up in a situation where the compiler is now tracking not only which registers hold which data stack items currently, but also where they might reside in memory. If we need to write back anything, or if we need to fetch them later. So as the compiler becomes more sophisticated, I may reunify the data and evaluation stacks, but right now I don't see any particular need to. And also the fact that I can focus the evaluation stack on just the CPU registers means better code factoring in the compiler itself, which is kind of nice. And because the evaluation stack sits exclusively in the CPU registers, that changes the characteristic of this stack substantially compared to, say, the data stack, or what you normally associate with a fourth stack. In particular, everything on that stack is ephemeral. If you make any control flow change whatsoever, if you call a subroutine, if you return from a subroutine, if you take a conditional branch, anything, that stack effectively empties. There's a good reason for this. And it's kind of explained in this paragraph here. Basically, if you try to execute, so we have this code here, this one foo fetch if blah, blah, blah. So depending on the value that's stored in foo, we could either drop this one and then push 3, meaning at the end of this word, we'll have the value 3 on the stack. Or we can push 2 and then push 3, meaning at the end of the word, we have 1, 2, and 3 on the stack. So if we treat the ephemeral stack, if we treat the evaluation stack as a persistent stack rather than as an ephemeral stack, by the time we get to this code over here, now here I have just a semicolon, but if we had something else behind here, where's the top of stack? And how does it know? This is a major problem. So I think what you'll find in most other solutions to this is huge quantities of compiler code intended to track where this information is. And you'll have like this implied chunk of code that the compiler spits out here that says, okay, if I go through path 1, it's in register x16. If I go through path 2, it's in register x18. So now I've got to unify this code and, you know, conditionally move registers and blah, blah, blah. And you can actually see this if you look at a single static assignment form. There's these things called feed functions. And they're not supposed to emit actual code, but they correspond to compiler points where the compiler scratches its head and says, okay, what's the best register allocation so that I minimize all this register juggling? That's one way of doing it. And it's a successful way. We know this because major compilers like GCC actually produce really good code nowadays. I take a different approach. I just kick that whole problem out. The idea is every time you take a branch of any type, just empty the stack or just assume that it's empty. This actually has some interesting connotations. Typically in Forth, you would treat the if statement as an expression. So I could say, for example, 1, foo if blah, 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 3, and then some mathematical operator, right? So I could actually affect the outcome of a calculation based on that if. If you empty the stack every time you take a control flow change, that if statement is now Well, it's a statement. I keep saying it without even realizing it. That if construct is now a statement rather than an expression, which means that you can no longer use this embedded inside an arithmetic computation. So that kind of subtracts a little bit from Forth's elegance, but at the same time, it keeps the number of lines of code in my compiler down to less than 500, which I think is a worthy trade-off. So the way we actually get around that is to actually use the data stack, which is here. And you'll notice these two Ds and from Ds, 2D from D. So the 2D and the from D work just like 2R and from R that you're already familiar with, in that it takes a value on the ephemeral stack and pushes it onto the data stack, or likewise takes a value from the data stack and pushes it onto the ephemeral stack. These actually correspond, if you were to look at the assembly code that this compiler produces, which I'll show you in a bit. These individual 2Ds and from Ds actually correspond to two instructions, a load and a store and a stack pointer adjustment. Now, the D sharps, this is just a parsing word that takes a value and pushes it onto the ephemeral stack. Correct. So the question was, this was just a parsing word, and that is correct. So D sharp will parse the 1 and will actually push will emit code to push 1 onto the stack. This is, when I say that this is compiled code, strictly speaking, it's not. It's actually interpreted in G4th, because I wrote the compiler in G4th. So there is no colon compiler per se. This is just parse the word blort, generate some assembly language, and then D sharp is another interpreted word that does kind of the same thing. That's correct. I was actually getting there. There's also an H sharp as well for hexadecimal numbers. And also the way that I do D sharp is kind of hacky. It invokes evaluate because I didn't feel like writing my own numeric conversion. So you could actually write D sharp $, and then a hex value if you wanted. But yeah, so but the point here is that we use these 2D and D froms to persist the values that we are interested in. So that's kind of the first thing that came to my mind. It's like, okay, well, if I do this, then it simplifies the compiler. Yes, there's a cost in the sense that it doesn't feel like traditional Forth, which kind of is sad, but it's still worthy of a price to pay, I think. Some possibly will disagree. And to show you that this is actually a viable approach, here is a program that actually does work. This is actually BSPL's very first program that it compiled, which prints out a matrix of characters on the screen. So this basically does your traditional ASCII dump, if you will. And the way it works, very simple. We push the value 0 onto the data stack. We execute, or we print out 16 rows, and then we deadlock. We hang the processor. Each row has 16 columns. Each column, we print a character followed by a space, and then we loop. Or I'm sorry, we don't loop. We increment that value. And then if it's, I use negative if here. We check to see if it's less than 32. If it is, here's an interesting construct. I pop from the data stack. I replace it with the ASCII code for a period. I push that onto the data stack. So at this point, I still have that old value on the eval stack, but there's a control flow change here. Gone. So remember that we empty that stack every time there's a control flow change. So even though we have this garbage value on the evaluation stack, by the time we get to emit, that value is gone. All right. So that was the first thing that came to my mind that had an impact on my ability to compile a machine forth. Another thing came to me by way of a friend online using intermediate compile buffer. Now this is probably at least as contentious in the Forth community as local variables, is the idea of using multiple compiler passes. It turns out that to generate efficient RISC code, you have no choice. You must use at least 2 passes. There's a very good reason for why this is the case. That reason is actually illustrated elsewhere. But before I get to that, I want to explain how this actually works and the way that I use it. So I have in the code, in BSPL itself, and I'll show you in a bit, a compiler buffer that is, if memory serves me correctly, 1024 slots or cells in size. Each of those cells has an 8-bit opcode and an extra parameter field, sometimes not used. So the actual compilation process, so if I come back up here, for example, if I want to compile this instruction or this line of code here, so D#0 will push an instruction lit followed by 0. Each of these R's here will be a call with a parameter field referencing this particular subroutine. Begin it again will be a jump instruction, and so on. So the intermediate compile buffer, when you first start compiling, is filled with basically a MISC-like representation of code. That's the first step. Now, it turns out that RISC, the primitives in a RISC processor and the primitives in a MISC processor overlap greatly. So you would think that it would be very easy and almost a single pass sort of way to compile to RISC. It turns out that the real reason why you want to have multiple passes has nothing to do with register allocation, has nothing to do with gosh, I'm blanking. Fetching and storing parameters from memory. It turns out that it all has to do with branch targets. It has to do with instruction formats and whether or not you have large versus small constants, because the instruction formats are optimized depending on the size of your constant. But here what I'm doing is I'm just treating everything as a finite uniform representation, which is what you would expect in a MISC processor. And these are the actual opcodes that I compile to. Now these are not actual machine opcodes, which you can tell because I have an instruction called label. Now this is probably one of the biggest innovations that has come across my desk. And it turns out that it predates my birth. There was a single board computer called the Kim, based around the 6502, which some folks in Germany decided to clone. They called it the Elector Junior. The people behind the Elector Junior said, you know what? Tapping hex codes on a keypad really sucks. We need a way to do multiple pass assembly on this same thing. Like they found a way to do an actual 2-pass assembler using a hex numeric pad for input and output. And the way they did that is they have they used an unused opcode in the instruction stream as this is a label. And what the assembler would do during the first pass is it would look for these pseudo instructions, note their addresses, collapse the program down 2 bytes 2 bytes or 3 bytes, I forget. And it would leave enough space at the end of the compile buffer for to build up a symbol table, and then it would go through and it would reassemble using that symbol table. Absolutely brilliant. And so this is the approach that I'm using here. And you'll see label defines a label index, and then I've got a bunch of things that actually use them. Call is a little different though. Call takes a string index, which there's no virtual instruction to define it, but when you do colon, when you execute the colon compiler, if you will, it will parse the forward word, and then it will stuff it in the string table, and it will assign it a string index. And so we've got rfetch and rstore, dfetch and dstore. These actually take cell offsets, which basically, if you can think of it as here, I'm going to break the cardinal rule, another contentious issue. I treat the data and return stacks as arrays, not as strict computer science stacks. So this is basically equivalent to something along the lines of you push a literal onto the stack, you add, and then you fetch. That all translates to one instruction in the final output code. And then, of course, I have an instruction stirlet, which actually pushes a string onto the evaluation stack as well. So those are the instructions that I deal with. So the entire BSPL compiler compiles in terms of those instructions. The structure of the actual compile buffer, though, is specific to the RISC-V architecture, and it could probably be used for MIPS and for a couple of others as well. What you have is you have this buffer here. You have pointers. I have buff, FI, and NI. As you compile code, obviously NI is where you're going to put the next instruction. But what happens if you compile a numeric literal? Well, remember what I said about literals being large versus small. On a RISC processor, you typically have 2 ways of getting data into the CPU. You have the ability to fetch from memory, or you have the ability to add a small constant usually to a register that is fixed in value to 0. So in the case of the RISC-V, I can add such a small constant in the range of -2048 to 2047. That's it. Any other value is off limits from that without having to resort to bit shifting and ORs and all sorts of other stuff. So the way I do that is, the way I handle numeric constants is I stuff the constant at the very beginning of the compile buffer, and then I shift everything down 2 cells. So all my numeric constants, regardless of size, are 8 bytes. So now FI, of course, advances down, NI advances down. So as I keep compiling, I get the earliest constants here, the most recent constants up here, and then the code, which if you recall up here in the we have this offset to constant. When we compile a constant that way, that offset gets compiled into that literal. And so that's how we know which constant we're referencing in that table. All pretty brute force, but it works well, and I don't have to malloc anything, which is nice. As I indicated, we use multiple passes. And the first one of these is global pointers. Now, remember that the compiler knows exactly where these numeric literals are located. The processor, however, does not. So whenever we make reference to a numeric literal, we have to tell the CPU where to find this numeric buffer. And it turns out, since I put it at the very beginning of the routine, ideally, we would like to say, okay, I want you to fetch from this offset from this particular label. It turns out that the RISC-V has a useful instruction called AUIPC, which stands for add upper immediate program counter. And if that upper immediate happens to be 0, it will add the value of the program, or I'm sorry, it will set your register to the current program counter of that AUIPC instruction. But you don't want to load that register all the time because you're just wasting time and memory by doing so. So what you want, the way I do it is I go through the compiler buffer from start to finish, and every time I find a lit instruction, I insert a hole into that code and I stuff an LGP instruction in there. So nothing that you type on the keyboard will generate an LGP opcode in the instruction stream, but a subsequent pass will introduce them on an as-needed basis. Labels and subroutine calls, like I said, that empties the stack. We have to also assume that it also corrupts the global pointer, because if I call a subroutine, that subroutine may use its own set of literals, and so the global pointer will be set to that subroutines instead of our own. So after we come back from a subroutine, if we make any control flow changes, we have to reset the global pointer as well. So we need to be sensitive there. Hence why we have an LGP here and an LGP here, but not here, right? So we're intelligent about where we place these instructions. Prologue and epilogue insertion. I don't have any convenient diagrams for this here, but I'll show you in code later on. When you call a subroutine in a RISC processor, I'm sorry, when you call a subroutine in a MISC processor, your return address gets pushed onto the return stack automatically for you. If you do the same thing in a RISC processor, that is not the case. In fact, I'm not aware of very many RISC processors that even have hardware stacks. So what happens is it stuffs your return address into a CPU register, and then it just leaves it to software to save that register contents as appropriate. And this works great as long as your called routine doesn't make any calls of its own. Because obviously if you try to do that naively, you'll just overwrite the contents of that register and you'll never be able to return. So prologue and epilogue insertion works by looking, it's actually two separate passes. The first one is a prologue insertion where all it does is it looks through the compile buffer for a call instruction. If it finds even one, it inserts the prologue at the very beginning of the program code where the FI pointer points to, and then it's done. That's all it needs to do. Epilogue insertion then notices whether or not the prologue insertion had happened. And if it has, it'll go through the compile buffer and actually look to see for every exit instruction that we compile, we have to restore our return address from the return stack. Otherwise, if we don't make any sub calls, there's no need to save the return address at all. The next step is we do register assignment. Now, this is actually the point where the MISC code starts to look more risky. And let me shrink down so that fits, right? So basically in our compile buffer, we start out with something like this. And by the time we're done, in the same amount of space, it looks like this. The idea here is that now we've got slots that we can assign registers to. And then, so everything that used to be over here and then we just use these extra locations for registers. Now, I maintain registers in a stack, obviously an ephemeral stack. And so the resulting code, it's interesting because just like the S16X4 that I used on the Kestrel 2, doesn't matter how complex the code I actually write. I I've so far never used more than 3 CPU registers. I actually have enough space reserved for 16 just in case, but I've never actually used all 16 of them. I haven't even used 4, let alone more than that. At this point, we now have a representation that's kind of half MISC, half RISC a little bit. This would be an ideal spot to put more aggressive peephole optimizations. And that basically just means more passes. I don't actually do this just yet, but there are plenty of opportunities. For example, if I push a literal constant on the stack, add that constant, and then fetch from the resulting sum, that is exactly what this RISC processor is able to do in a single instruction. Similarly with stores as well. So I can recognize, if I can recognize this pattern, so this would take 8 bytes, 12 bytes. This would be another 4 bytes, that's 16. This would be another 4 bytes, so that would be 20. I would basically reduce a 20 byte sequence down to just 4 bytes by doing this. And and this is just representative example. There are other examples where I can say, okay, this chunk of code can be more succinctly represented as 1, maybe 2 CPU instructions instead of a whole sequence of them. And then finally, the very last pass, we generate an assembly language listing. Now, if we were to make an interactive forth environment, instead of generating the assembly listing, we would actually just convert this straight to binary and then compile the resulting code at the here pointer that most forth people would be familiar with. But since I'm actually targeting separate compilation for the purposes of building system software for the Kestrel, I generate an assembly listing at this point. So what does BSPL look like? Well, let me show you. So I wrote a program called SD Test because I'm actually also working on an SD card emulator for the Kestrel emulator. And as you can see, this looks an awful lot like forth. Except there are a couple differences. So in particular, here's a statement called extern. And what extern does is it basically tells the compiler, don't worry, this label does exist. Please don't throw an error when I reference it later on, which of course I do for both pass and fail. In this case, the mu_exit is a subroutine that I hand wrote in assembly language. I have these 2 constants here. Those are specifies addresses right now for in the computer's I/O space. Here's a routine. Here's a routine that basically waits for you to hit a key on the keyboard. And then I've got emit and type, which are fairly self-descriptive. I have some routines that actually prints out hexadecimal numbers to the screen. And then I've got an SD card, basic SD card driver. Transmitting a byte, receiving a byte. I mean, this is all fairly self-evident, and this is all hosted on GitHub too, so if I'm scrolling too fast for you, that's okay. I do have everything up on the web. So as you can see here, I mean, here's an good example. Here's H#. I'm using hex codes. I push it onto the data stack to make sure it persists across the subroutine call. You know, I've got all this stuff, and then here I basically drop the return because I don't need it. But then you'll notice here it's like I don't have any actual numeric constants, so it just looks like normal forth. And I find that when I code like this, I find that I have two types of routines. One where I do computation and one where I do predominantly control, which is you do this, you do that, you do this, you do that, and then I'm done. I may have a conditional every now and again. Where things get kind of ugly, for example, is in this SD param, where I have to use 0 defetch, write out a byte, do the same thing, write out a different byte, do the same thing, write out a different byte. The reason why again, I can't use the dupe operator here, because if I do dupe, yeah, it'll duplicate into another register, but then when I call the subroutine, those registers are empty, right? So I have to emulate dupe onto the data stack manually. So there it kind of loses its elegance a little bit. But as you can see, just generally speaking, you know, this is a pretty forth-like code. Unlike the Kestrel 2's assembler, I actually have direct support for S-quote, so I no longer need custom specific words for compiling strings, which is awfully convenient. And you'll notice that I just do when S-quote executes, it actually pushes the address and the length onto the eval stack in opposite of ANSI order. So when I do 2D 2D, it's now in proper ANSI order. So it pushes length address. 2D 2D, now it's in address length format in memory. So type and such can preserve the ANSI semantics where there's no need to change it. So let's go ahead and I'm going to go ahead and build this code. I'm going to cheat, and I'm just going to. Oops, what happened here? Redo. What is going on? There's the test.asm. Oh, I have not built this. Well, this will actually build it too. It's actually building the all the ROM images right now. What's that? The build system is called Redo. And it is a, I need to copy paste that. So now I can do source. Yeah, and there it is anyway. But if we look at the generated assembly code, so here, for example, fail, we push, since we are making a subroutine call, we actually do save our return address on the stack, even though we don't have anything explicitly doing that. So we're referencing a literal, so we're grabbing the address of our program counter, which we use in the computation to reference that. We call our exit, which never returns, but Forth isn't smart enough to figure that out, so it generates the epilogue code anyway. But if we go, for example, down here into the ready loop, you'll see that we don't store our return address. There's no point in doing so because we don't call any other subroutines. But we do reference a literal, so we do use the global pointer. So we fetch a byte, or we load the address, I should say, into x16. Here we fetch the byte, and then we do our branches. And you'll notice that the branches are actually comparing and branching as though I would write this in by hand. It's not exactly as elegant. For example, if I do the less than, like if I want to try to compare something against another value to see if it's less than or greater than or equal to, it doesn't quite compile as efficiently for that. There are ways of getting it to do that. But for now, this works. So yeah, I mean, this is this is pretty good code. It's not spectacular.
For short, you are actually in the short constants, or
I am not. No. So short constants will come a little bit later. I just wanted something that worked. To add support for short constants, I would need to add a new bytecode for that and make the appropriate adjustment in the first pass, the compile pass. And then I would need to funnel that through the other passes, which I can show you here in a bit. First, what I would like to do though is actually prove that this actually works. Oops. I really got to fix that bug. So let me create an SD card image, which is empty. What is going on here? I have SD test. Why is this suddenly not working? In E, ROM file. Oh, because I didn't include that. Okay, so it thinks, so now it's going to do its little thing here. Everything seems to work. So now we do this, and now we suddenly see that we have data in our SD card image. So if we do a dump, yeah, we see that there's test patterns and such inside. So something maybe a little bit more, so if I do source, let's take a look at some BSPL inside the examples. So if I do redo, right, so very simple again. So if I do, this is not the best keyboard. And it prints out hello world. And the code for doing that is there. So taking a look at the insides of the compiler itself, if I have time, I've got 15 minutes. So here I broke everything up into separate modules, which I include. Here's the definition of extern, which I showed before. This actually forms the core of the colon compiler, actually. So let's see here, pass one. So basically, when I invoke the colon compiler, that delegates to this pass one. Colon 0 and it basically zeros the compiler state, and then I execute extern to define the word or to declare, hey, there's a word here. And then when I execute semicolon, I compile a return. I compile a return from subroutine at the end of the definition, and then I execute passes, which, as you can see just above, here is our list of compiler passes. Insert the global pointers, insert prologue, insert any epilogues, perform register allocation, generate assembly code. And that's it. We're done for that definition. And if we look inside our individual components, so basically we start off with a fairly traditional looking MISC style assembler. I have a lot of comments, as you can see. So there's the definitions for D sharp and H sharp. Here's some of the instructions that we compile for memory stores and fetches. Here's some of the arithmetic and logic. Control flow, which I then use to build up bigger primitives such as if statements, while, repeat, until. I have begin again. So your subroutine support. And then here's our data stack accessors and our return stack accessors. Here's our stack permutations. Now, these stack permutations, which I haven't illustrated here because I really haven't had a need to, per se, these only affect compiler state. They don't actually generate assembly language. So if I load a value 1 and a value 2 in the CPU registers, it'll assign x16 to 1 and x17 to 2. But then if I execute swap, it doesn't exchange the contents of the registers. x16 will still contain 1 and x17 will still contain 2. What changes is the compiler's understanding of which register corresponds to the top of stack. Right? So that in that way we basically compile out most, if not all, of the stack permutation operations. Bit shifting. Here we are declaring variables globally. We have bytes, half words, words, and D words, as well as anything arbitrary length in the form of a buffer. Here's our support for strings. And that's it. So that's the first pass. As you can see, it's predominantly concerned with filling that buffer, which we would expect. LGP is the pass that's responsible for inserting the LGP operation where necessary. And basically it stores, let me jump to the bottom here. So basically the way it works is we basically loop from, we start at the first instruction and we maintain a variable CI to keep track of that since we don't want to change that by. And we just loop for every instruction in that buffer, and we just execute question insert on that instruction. We classify that instruction depending on how do we want to ignore it, do we want to insert it, do we want to reset our state, and then based on that, if we need to insert, we will we'll register this flag saying that, hey, we've done the inserts. We will vacate a space for that instruction, which I will then store, and then I will increment the NI pointer. So vacating that hole in the program, we have to adjust the NI pointer because otherwise you'll overwrite the tail end of the program. So as you can see, let me, I don't know if you can read this here, but basically this whole pass takes 61 lines of code. That's with comments. Let's see here, prologue and epilogue. These are so short that I actually, the two passes are so short that it takes 29 lines of code. And basically it follows the same pattern again. You know, we basically start at the beginning, loop for every instruction, and if we find what we're looking for, we react to it. And this is all reasonably well commented. Oh, this inserted variable, we actually depend on that from the previous pass in order to keep track of whether or not prologue actually did its job, or not did its job, but if it detected the need to insert a prologue, which we then use later on down here Here we go. Inserted fetch if. So right. So basically, we'll completely skip that that third pass if we didn't bother inserting any prologue. So register assignment, same idea. Start at the beginning, and then we dispatch based on instructions that we find. Now here I'm using a jump table because it just is easier, and then I classify the format of the instructions. And basically it goes from no op down to stirlet. And so for each of these types of instructions, I either shift or I either don't do anything, or I'll shift and make room for registers, which I'll then say, for example, top, whatever the compiler thinks is in the current top of stack, that becomes the first register for this instruction slot. So basically this is just saying, okay, at this point I'm actually keeping track of which register the compiler thinks is the top of stack, and then treating it accordingly. And then ASM is the assembly generator. Same idea, same loop. I have a little bit of extra code here to handle the boilerplate. So for example, at the very beginning, I want to generate an alignment so that I always generate code on an 8-byte alignment. I emit our list of D words that correspond to our numeric literals at the very beginning. I generate our label for the subroutine, and then I generate the actual code. The actual code is what actually loops across the instructions, jumps through all these different representations. And now, because of the changes in thought process, now take a look. The vast majority of instructions all correspond to one assembly instruction, which is what you want for a machine fourth compiler. That's the whole point behind a machine fourth compiler. The only big ticket, the big heavyweight instruction here is stirlet, because this actually compiles to a sequence of instructions, because it has to load 2 registers and it has to embed string constant into program memory in order for that to happen. So that's kind of a complex operation, but everything else, it's all one instruction. And as I indicated before, I go into examples. Right, so here you can see individual things. Like here I'm referencing a numeric literal, that's one instruction, although we do LGP as a prefix to that. We add a constant because we're getting a hex value here, I believe. Yeah, next character, right? We push this onto the stack. That's two instructions. So except for string literal, nothing exceeds 2 instructions. And we can see that it properly handles jumping around in a loop. Right, so we at the end of the loop, we jump back to L0, which is up here. And then here, if we're at the end, we'll jump down to L1. And you'll notice that it's reusing all the CPU registers. I'm not leaking registers. That's because every control flow, I empty the state of the evaluation stack. And then here's the actual, here we actually see what the stirlet compiles to. Basically, we do a subroutine jump down to this address down here, but instead of using the normal return address register, we use one of our data stack registers. So now we've got the address of the hello world in that register. Then here, here's an example of using the short constant, the add I x16 x012. That's the length of the hello world string in this case. And then I have the little 2D. This is these 4 instructions here. So decrement data stack pointers, store, decrement data stack pointer, store. We type, we return, we generate a line feed, we terminate the program. Right? So it's all, you'll notice that it's surprisingly compact, considering that we're compiling forth into RISC code, a register machine. So I would say in terms of efficiency, I would probably compare this to C compilers circa 1983, 1984 in terms of code quality. And the complete and total number of lines of code, excluding comments, well, let's find out. So if I do that, and I say, I do not want leading comments, and I do not want empty lines, and I count the number of lines, I get 455 lines of code. So this is on par with the MUP21 machine forth compiler. I'd say maybe a factor of 4 bigger, just to account for multiple passes and other necessities that are unique to the RISC environment. But that's still the same order of magnitude number of lines of code. And that's BSPL. Any questions? Yes?
Have you considered with the evaluation stack, you're able to make very dense code as long as you sort of do the right stack densities.
Mm-hmm.
But I'm assuming that if you hit the return stack with anything, you're going to actually hit the return stack. But you also have a sort of evaluation return stack.
No, the RISC architectures do not have a stack. There is no return stack in RISC. Everything is handled by registers. Yeah.
Well, or put it this way, if you had an evaluation of a compile type return stack, you could potentially have code that does more shuffling without having to reach deeper down. Although I guess you said you would never gotten deeper than about 3 elements.
Yeah, so I've never gotten, so the question was, if we use to_r and from_r to temporarily save the state of the evaluation stack, then we can, and if we do that and on top of that maintain a compiler understood view of what the return stack is, like a compiler eval stack. I'm sorry, a compiler return stack, I should say. There's 2 problems with that. One is, what does to_r mean in this case? Am I actually stuffing it to the in-memory return stack, or is it to the compiler, right? And so I would end up having to make another set of accessors. The other thing is, yes, what you're saying is correct. I would be able to avoid stack permutations and stuff, but to date, I've never used more than 3 stack items, which means that rot is actually plenty sufficient for my needs. Also, if I need to push something onto the return stack, it's usually to manipulate the return stack frame. So for example, in an earlier discussion, Bob had asked, does forth have a select statement or something along those lines? And the answer, of course, is no. But if I needed to, what I would do is I would list out my words. I would say, you know, here's condition 1, condition 2, condition 3, and then here's my default, right? That would all be part of 1 colon definition. But if you interpret this literally, this looks like I'm executing all 3 conditions followed by the default. So how do I avoid that? The way that I would do that is, of course, return stack manipulation. And that's actually something that I've documented before. That's up on my website.
Using the returns, you're using the fact that it's actually the return stack as opposed to.
Correct, yep. And BSPL is actually still evolving. There's a number of things that it still cannot do, like, for example, compile jump tables, which for me to port over STS from Kestrel 2 to Kestrel 3, I will need that functionality, but I just haven't needed it yet. So this will definitely grow. Code quality will improve over time as needed. So my immediate goals with this is to port over the STS operating system from Kestrel 2 to Kestrel 3, and then get that functioning, and then find a way to get or write an ELF loader, an ELF binary loader. That will give me the ability then to use the RISC-V development tools that are native to Linux. For example, GCC toolchain. I can use GCC to write C code at this point. So anyone who wants to hack around with the Kestrel using C, now, even though I'm writing the OS in a 4th language, now they can use C or C++ to write their code, right? And so that would be probably of great interest to a large number of my followers at this point, because not everybody follows the 4th path, but, sorry, I keep hitting the microphone. Not everybody follows the 4th path, but I know that a number of people are still interested in the project anyway. I've had a number of people ask me, you know, oh, are you going to support Linux on it and stuff like that? And of course, my response is, I would love for someone to port Linux to it. It just won't be me, right? Because Linux is just really, really complicated and hard to port. So for now, I'm sticking with the simpler runtime environment. But if I can leverage GNU tools outside of STS, then that would be convenient. Yes?
Another question. You go into great lengths to build sort of constants for large constants. Did you consider just baking that into the constant word and then sort of some, I guess you have to pay the cost of the jump and return, but you've got.
You still need to do the constant juggling. The CPU itself has no way of loading a large constant into a register. Oh, you mean like I did for strings, where I jump over the constant? Yes, it actually takes it's slower at runtime, and it's actually somewhat more complicated in the compiler, because what you have to do, you have to remember when accessing constants to align the data. So what ends up happening is you'll jump over the constant, and then you have to do an add 3 and -4 in order to round up to the next, or I'm sorry, add 7 and -8 to round up to the next D word boundary, then fetch from there. So it ends up being kind of hokey pokey. Yeah, it's not very elegant. It's much more, it's much easier to just have the constant pool and reference it via register that way.
Last question I have.
Yes.
I looked up the redo. Have you had positive experiences with it so far?
I've had nothing but positive experiences with it. I know that it has faults. For example, a redo target. So the question was, have I had positive experiences with redo? And of course, yes. I've had nothing but. But I also know that it has faults with it as well. So the big problem with redo for a lot of people is a single target can only build a single file. This is a problem that make does not have. You can actually have targets that generate, or commands that generate multiple targets at once. But for my needs, redo is plenty sufficient. The reason I use redo instead of make is primarily I can keep the build targets in the same directory that the build artifacts go. So for example, if I take a look at, if I come into examples and I take a look at, for example, I look at the default ROM do. So to actually build the ROM file that the emulator runs, I have this, the first line here, this redo if change. I'm listing all of my dependencies there. And this is just a shell script, by the way. So I can do all sorts of weird environment variable munging and stuff. And then I actually invoke the assembler on the assembler on the generated ASM file to the generated ROM file. And that's basically how I generate the ROM. Now, for people listening online, that's probably a lot of pronouns. I apologize, but and it's the same thing here. Basically, I say I'm going to depend on whatever .bs because that's the BSPL's source, and then based on that, I will invoke the BSPL compiler, right? So if I generate individual targets this way, one way that you can handle multiple targets with redo is you basically define a meta target in a way where I say these individual targets all depend on one meta target, and that meta target is what's responsible for generating all these other things. The problem with that is you end up with garbage meta files and stuff, right? So there's ways that you can do it. It's not entirely elegant, but in Redo's defense, you'll only be able to, at least in my experience with it, I've never had a need for it, first of all, but how many times do you build multiple targets at a time, right? It's very, very rare, less than 10% by far. And the fact that this whole thing is running entirely in shell script, I mean, Redo itself is written in Python, but yeah, and it's very, very small, very compact. Cool. So people are leaving now, so I'm going to sign off. Yes, it's over.